Good morning and welcome back. We will continue with the course by Professor Bernhard Müller. The third lecture will start now. Bernhard?
Yeah. Thank you very much. Can you see my screen? Yeah. I hope.
Yes.
Good. Yes. Good. So welcome back. So today we're going to move away from the mechanism of supernova explosions and start to focus on the multi-messenger signals that we can get to learn what's actually taking place inside a supernova. If we're very lucky, from neutrinos and gravitational waves from a galactic supernova, that would be the most intriguing discovery that we could hope for. Yeah, so we'll try and go into gravitational waves and neutrinos today. Based on feedback that I got, we might stretch this beyond today's lecture and rather go a little slower and perhaps cut down the Friday lecture on supernova phenomenology a bit in order not to rush things too much. Yeah. Good. And please do interrupt frequently, as always. Ask questions in the chat. And I've also been reminded that it would be good to repeat questions from the chat. If I forget, please do remind me again. All right. So let's see. First, as usual, you'd probably like to hear about a few references that allow you to read up on what I'm saying in more depth. There are a few good reviews on gravitational wave emission from core collapse supernovae, a recent one in this handbook here, and several ones on neutrinos in core collapse supernovae with slightly different emphasis. My ARNPS article is more focused on the emission of neutrinos and the signal, a physical interpretation of the signal. Mirizzi is very broad, also covers intricacies of neutrino flavor conversion, and Scholberg 2012 is a very good one on the actual neutrino detection. So let's start with gravitational waves. This is a summer school on gravitational waves, really, so I think I should give this priority. So let's first ask ourselves, why do core collapse supernovae emit gravitational waves in the first place? So I guess you've all come across the Einstein quadrupole formula at some point, I hope. So the Einstein quadrupole formula says that perturbations, wave-like perturbations to the space-time can be related to the second time derivative of the mass quadrupole moment. More precisely, it's the symmetric transverse trace-free component. The actual tensor arithmetics is a bit less of a concern here on this phenomenological level. And that means whenever we have matter that's not distributed in perfect symmetry and undergoing accelerations, then we'll have gravitational wave emission. It is very useful to break down the quadrupole formula using just dimensional analysis. The quadrupole moment, by order of magnitude, that's going to be proportional to the mass that we're considering. So the mass, let's say, of the matter inside the supernova shock times the characteristic length scale squared. And the time derivative introduces a factor frequency squared. And of course, this will hugely overestimate the actual amplitudes if the matter is only mildly deviating from spherical symmetry. So there's going to be an asymmetry parameter, which is in core collapse supernovae much smaller than 1, that we actually have to find out from simulations or from good physical arguments. Now we'll go through the various physical phenomena that give rise to a changing quadrupole moment in more detail, but just as an overview, you can basically classify the processes in, let's say, 2 or 3 different classes. So the one obvious way towards a changing quadrupole moment is to have a permanent deformation of the core in the presence of rotation. And if that core then collapses and bounces, you'll get a gravitational wave signal from the change of that, the quadrupole moment of that deformed mass configuration. That's probably the oldest scenario for gravitational wave emission in supernovae, and it's by now a very well understood one. Something which we have learned to understand better only in more recent years is the gravitational wave signal that comes from all these from the convective turnover motions and the sloshing motions of the shock that I showed you yesterday. Yeah. So you have plenty of aspherical, non-spherical hydrodynamical flow from convection both inside the neutron star, in the heating region, and you have the shock oscillations and possibly even some other instabilities at play. Yeah, that will also lead to changes in the quadrupole moment. And finally, there's another class of non-radial instabilities that's again related to rotation. So rotation by itself does generate a permanent quadrupole moment, and that will generate gravitational waves if this deformed mass configuration shrinks or re-expands. But you can get even more powerful gravitational wave emission if the rotation is fast enough to give rise to some non-axisymmetric triaxial instability. Yeah, and in classical fluid dynamics, we know that such asymmetric deformation will take place if you have a self-gravitating fluid that rotates very rapidly. Ellipsoidal deformation, already discovered in the 19th century, but that requires very rapid rotation. And it has been realized that even for, well, still rapid, but not nearly such extreme rotation, you can get triaxial instabilities in supernova cores as well under certain circumstances. And those would make usually much stronger gravitational wave emission than you'd get from expansion or contraction or expansion of a permanently deformed quadrupole alone. Yeah. Okay, let's quickly stop if there are any questions up to this point, whether someone hasn't seen the quadrupole formula yet and still wants to think about that a bit or so.
Bernhard, how about oscillations in the new formed compact object, including black hole? Can you get significant quasi-normal modes from the newly formed black hole?
Mm-hmm. Yes. So for black holes that you form in core-collapse supernovae, I should say honestly, no one has simulated that in multi-D consistently yet. So whether any asymmetric accretion flow through a disk will excite quasi-normal modes of the black hole, you can't quantify that by simulations yet. I do suppose, however, that because compared to, let's say, the massive amount of mass that moves around and collapses in a short time in a neutron star merger, let's say after the from black hole formation from a hypermassive neutron star, compared to that, the perturbations that you expect on your black hole from, let's say, a collapsar disk that's accreted by a black hole will probably be not very strong. they might be swamped by the gravitational wave signal from the matter around. So I think that probably space-time perturbations, perturbations of the vacuum alone, the black hole, will probably not be so important. That is a very good point when you consider neutron star remnants. Then the oscillation modes of those neutron stars will be seen in gravitational waves, and we'll discover later on that, in a sense, the primary role of the asymmetric flow in convection is very much to excite such modes. Yeah. During later stages, there might be different ways to excite those modes. So if you're talking about differentially rotating neutron stars, you could think about some R mode instability or things like that, or you could have modes excited by differential rotation and magnetic fields, kind of torsional modes. That's actually a very advanced subject that I can't cover in full in this lecture. But especially during the later stages, the mode, we will see that, in a sense, the gravitational wave emission mostly comes from some sort of mode excitation by these hydrodynamical non-radial flows. And the mode structure during the later stages that could contribute to emission can become a bit more complicated than during the early phase, where you're basically seeing one dominant mode, as I'll show a little later. Then there was a question, someone asking what I mean by triaxial instability. I might probably make a little drawing on this. Yeah. So the thing is the following. If you have, let's draw. So if you normally, let's say if you have a self-gravitating fluid, yeah, and that doesn't rotate, it will take on some spherical shape. Yeah. That minimizes the overall energy of the system. If this rotates, then what you'll have is that basically the centrifugal force will make it more favorable for some matter to be pushed away in the equatorial plane, and this will give rise to an oblate distribution of the fluid. Yeah, but it's still gonna be spherically symmetric. Yeah, so it's rotationally symmetric around this axis here. Yeah, but if rotation is fast enough, then already for let's say a homogeneous self-gravitating fluid, you can show that the actual configuration that will be preferred energetically is sort of a cigar-shaped true ellipsoid. Yeah, we're talking here about the Maclaurin ellipsoids or spheroids. Yeah, so it will become energetically more favorable to have the fluid distributed in this cigar-shaped pattern, where you're extended further in the equatorial plane in one direction than the other. Does that explain the question? To at least understand what a triaxial instability is? Yeah. So the mathematics behind it is a bit complicated, because you'd have to minimize the energy of this system depending on the radius of the ellipsoid. There are long-winded calculations in old textbooks, but what happens is basically that at sufficiently fast rotation, your fluid wants to take on a cigar shape rather than just an oblate rotational ellipsoid form. Yeah. And for classical homogeneous self-gravitating fluids, this happens at relatively high values of T over W. So T over W is rotational energy versus binding energy W. And I think, but I might recall these numbers incorrectly. So for the classical Maclaurin spheroids, you hit the instability at about 0.27 or something. But if you have a more complex stratified differentially rotating fluid, you can actually hit this instability at low values of T over W, the ratio of rotational energy to binding energy of just a few percent. That's what this low T over W mode here means. Yeah. All right, are we ready to proceed to the next slide? Yeah, let's go on. So let's first talk about the rotational bounce signal. And I should preface this entire discussion by saying it's now, so in some parts of the discussion of the gravitational wave and neutrino signal, we have to be a bit less quantitative. We can still be quantitative by looking at plots, but it's a bit less more difficult to actually give you simple scaling relations for why the signal looks a particular way. Yeah. But so let's first see what this rotational bounce signal does. So the scenario here is that your progenitor ion core is rotating. It collapses and it bounces. That makes for a change in quadrupole moment, and the second time derivative will dictate what the gravitational wave emission is. So shown here for a supernova distance at 10 kiloparsecs is this characteristic signal from a rotational bounce. We now know that if you use realistic microphysics in these calculations, this bounce signal always has a very practically uniform characteristic shape. So it's such that strain times R always has this characteristic little dip at the beginning and then goes down, and you have a second peak on the at positive amplitude again, and then you get a bit of ring down. Yeah, and that piece here is very universal for at least a given nuclear equation of state of the proton-neutron star. It basically looks the same regardless of how the progenitor rotates initially. Yeah, it looks the same, it has the same shape, but it will have higher amplitude if the progenitor core rotates faster. You only get exceptions from these for very, very rapid initial rotation in the progenitor core. And what you see here now are the characteristic frequency and strain of this signal for different progenitors, and actually two different equations of state, if I remember correctly. The ones with a slightly different color here, yeah, are different equations of state compared to the sensitivity curves of LIGO, advanced LIGO, and the zero detector, which people actually discussed at the time. That's, I think, I don't recall, but that's what might later have turned into the plans for the Einstein telescope. I don't know. I'm not the expert on this. Maybe someone in the room can say what actually became of Euro. But the key thing is you always get the very same or the very similar shape of the signal, almost invariably, with so it's just really one big peak with two oscillations before and after. So you can't really pin that down to a single frequency, but the entire spectrum has a very clear peak, a very clear characteristic frequency, which is of the order of 700 Hertz. That varies a bit depending on the equation of state. And this can be tied down to the fundamental oscillation mode of the neutrons, this very small young protoneutron star at this time, this frequency. Yes, and the fact that you have really a very robust signal means that you can actually use template-based searches to filter out, to discover this bounce signal very efficiently. And let's say if you have at least moderate progenitor rotation, you can hope to detect such a rotational bounce signal well within our galaxy with advanced LIGO, so to a range of about 40 kiloparsecs, and you extend that by at least an order of magnitude with third generation instruments. And the nice thing about this is because we understand the nature of this signal so well, well, the power or the amplitude that you measure and that you can extract by fitting your template is very nicely connected to the initial rotational state of the progenitor. So there's an almost linear relation here, well, or a good parallel relation between the initial ratio of rotational energy to binding energy of the progenitor core and the amplitude in gravitational waves that you get out. Yeah, and if you use realistic signal pipelines, you can actually reconstruct your beta ratio of rotation energy to binding energy in the progenitor core with rather good accuracy. Yeah, let's say on the 10% or tens of percent level. That, of course, has significant scientific potential because it would give you a true measurement of how fast the progenitor core of a massive star rotates if we have a galactic supernova. And this is something that, as we discussed in the previous lecture, is really an open question in stellar evolution, and we have no other direct way to measure that. Okay. Now, questions about the rotational bounce signal.
Can you hear me? Yeah, I think you can.
Mm-hmm.
So I had actually one question which came up actually yesterday in the tutorial as well. So in the tutorial yesterday, we were asked to find out the spin of the neutron star and then sort of apply a angular momentum conservation and find the spin of the progenitor. So there, of course, we're assuming that all the angular momentum gets transferred to the object. So my question was, what is I mean, how much amount of angular momentum is carried away by the ejecta, neutrinos, etc.?
Ah, yes, that's a very good question. So the short answer is that during the collapse phase, so up to bounce and shortly after bounce, you can apply this concept of angular momentum conservation. So what belongs as angular momentum to up to a certain mass shell in the progenitor will be conserved during collapse. If you're talking about longer timescales, the explosion phase, you're absolutely correct. There will then be transport processes of angular momentum that can take angular momentum out of the neutron star and distribute it into the ejecta, or you can also vice versa. You can actually spin up stochastically your protoneutron star by these asymmetrical motions around it. Yeah. This is actually a hard question. So it may very well be that, so for so unless for rather moderate rotations, or unless your progenitor already rotates with a spin rate of 1 second or so, which would translate into millisecond spin periods of the neutron star. So if your progenitor rotates slower than that, then the spin evolution of the protoneutron star may be completely determined by stochastic outflows and downflows. Yeah, and any memory of the initial rotational state might be erased in the explosion. Yeah. If your progenitor core rotates very fast, so giving you millisecond periods, then let's say stochastic fluid flow will have a harder time spinning the neutron star up or down or tossing the spin axis. There are certain instabilities that can still do that. So you may have significant spin down of a core that initially has a lot of angular momentum. You can have that, for example, by this standing accretion shock instability. If you go to a very fast regime where it transitions into actually a triaxial spiral instability, that could spin down the neutron star quite a bit. And you could spin down the neutron star quite a bit if you generate strong magnetic fields. So if you actually have strong magnetic fields that extract the rotational energy of the neutron star efficiently, then you might start, let's say, with a 1 second core period, spin period. After collapse, you might go into the millisecond regime, spin period regime for a while. But then as the magnetic fields act, you spin down the neutron star into the regime of normal spin rates of pulsars or even slower. No one can really tell.
Okay, yeah, and one small question on the plot on the right. So that is presumably from numerical simulations, right?
Yes, so what this is this one here basically uses gravitational wave templates from numerical simulations. They're injected into the signal simulation. Yeah, so you make a noisy signal. You try to then do your matched filtering, and you say what value of beta do you recover, and how does that line up with the value of beta that you actually had in your model?
Okay, thank you.
So Bernhard, here in this plot, the progenitor refers to the iron core, not the star.
Yes, that refers to the rotation of the iron core. Yeah. Mm-hmm. Yeah. I get a few more questions in the chat, which are good ones. So the first one is, how will we account for wobble in the rotations? Won't it affect the signal? Yes, on longer time scales, you will get these wobbles because of asymmetric accretion flow onto the neutron star that can toss your spin axis around a bit. That's not expected to happen already with the bounce signal. And later on, yeah, this will affect your gravitational wave emission, but you can't really put your finger on it. You don't have a smoking gun for that in the signal. At least no one knows one yet. Yeah, that's to be found out, whether you can find a signature for the wobble of the spin axis that may occur in some models. Then there was another question about whether the rotation of the neutron star is uniform or differential. So in general, you'll get differential rotation. Yeah, even if your progenitor core rotates relatively uniformly, this will not be conserved during the collapse, and the protoneutron star will develop non-uniform differential rotation and retain it over, let's say, significant time scales. In the end, at some point, magnetic fields will want to bring the neutron star into uniform rotation over long time scales, but what the time scales for that are depends on physics that we don't completely understand yet. Magnetic field amplification, magnetic stresses, and how efficiently they transport angular momentum, and so on. Then there was another question in the chat whether the dip corresponds to the stalled shock. You mean probably the dip here, the negative dip in the amplitude. Yes, that is actually not from the stalling of the shock. This is really the the turnaround of the contraction of the core by the stiffening of the equation of state. You don't see so much of a signal of the stalling of the shock here in the gravitational wave signal. There is an indirect effect, somewhat indirect effect, because shortly after the stalling of the shock, you get what is known as prompt convective overturn behind the shock, because the entropy gradient changes such that it becomes convectively unstable. And that is reflected in this more stochastic, more chaotic signal pattern here. Yeah, but you don't really get a direct signature of the stalling of the shock. Okay. Now let's move on to the signal from the later phases. Yeah. So, well, we know we have a lot of non-spherical fluid flow developing later on during the evolution from the bounce through the accretion phase to the explosion. And I'm going to show you right away what it looks in terms of amplitudes. It looks a bit chaotic. You can still robustly identify certain features. This is for an old 2D model, which just happens to show these components very clearly. In 3 dimensions, the amplitudes tend to be lower, but the overall signal structure is rather similar. So the first signature after the core bounce that you get, if you have no rotation, is this prompt convection signal that I just mentioned previously. So so behind the shock, your entropy gradient actually becomes convectively unstable. That's not related to neutrino heating in this early phase. This is really simply the slowdown of the shock and how that slowdown changes the post-shock entropy that's responsible here. And then what happens is that this convection dies down, and in leaving over, in dying down, it excites pressure modes with a specified frequency of the order of 100 Hertz. And you see that ring down of these pressure modes excited by the prompt convection here. Then you'll get a rather quiet phase for a while, and about 100 milliseconds after bounce, typically you see the neutrino heating becoming vigorous and starting convection fully. That's when you start to get more gravitational wave emission again. And this signal now just looks very stochastic superficially. Yeah. At about a similar time, you often get the standing accretion shock instability kicking in, and that will create patterns that will actually be a bit more regular. We'll see that later on. Now, this gravitational wave emission then tends to intensify if you develop an explosion, if the shock is revived and the convection is happening in a larger gain region containing more mass and with higher convective velocities, then the gravitational wave emission intensifies for a phase of a few hundred milliseconds, 100 or 200 milliseconds or so. And as you go into the explosion phase and the accretion flows onto the neutron star become weaker, the gravitational wave emission tends to subside, doesn't subside completely. You still get a low level of this noisy signal here because there's still motions in the protoneutron star that are forcing oscillation modes in gravitational wave emission. Yeah, and during this late phase, you also tend to get a bit of a tail signal. So this is related to a memory effect for the gravitational, no, sorry, this is related for a memory effect from the expansion of an asymmetric shock wave. Yeah, you get a similar tail signal, similar memory signal from the asymmetric emission of neutrinos, which is usually much larger than any tail signal that you get from the asymmetric expansion of the shock. It's probably advisable if we now go to the next slides already, because I'll go through these signal components and you can ask questions on them individually. Yeah. So, and let me, if you just bear with me for a minute, I'll get some fresh fluid. So on the previous slide, the signal initially just looked very, very noisy, right? So you could say that it's peaking in amplitude around the time of shock revival, but it was hard to see a very, very clear structure in that. Now, normally when something like that happens, what you try is to find structures, maybe not in the time domain, but in the frequency domain. Yeah, so we can look at the spectrum. This is the spectrum of, I think actually this particular model here. Yeah, and what the spectrum basically tells you is that most of the energy of gravitational waves is radiated away at frequencies of several hundred hertz, above 500 and in the vicinity of 100 kilohertz. There's often a broad hump at low frequency that may be related to this prompt convection, or it may be related to the standing accretion shock instability. But a spectrum, a time integrated spectrum, still doesn't show very clear structures. Yeah. But there is actually a much more well-defined structure underlying this signal. And you see that if you do, instead of a spectral analysis, you do a time frequency analysis. And you already see that if you zoom in onto the short snippets of the amplitude. Because what you see is that the amplitudes here, they vary stochastically quite a bit, but there is really a well-defined oscillation for a period and frequency here that you can see. Yeah, and if you go to the time frequency domain by doing either a short time Fourier transform or a wavelet transform, you start to see definite patterns. So if you do a wavelet transform of this signal here, what it starts to look like is this. So you can actually identify something at the very beginning, which is really this early signal here from the prompt convection at 100 hertz. And you can identify another clear emission band with increasing frequency with time. Yeah. That's really quite well defined. Now, let's see where this comes from. I'll summarize what we have. So this is just a summary really of what I said before, right? So we'll have the signal components that we usually have is an early signal, 100 hertz about after bounce, which is P modes excited by prompt convection. Then we'll get a signal from convection and SASI later on. And if we explode, we get a tail signal from the asymmetric expansion of the shock. And we often get a tail signal growing offset in the strain from the memory effect of gravitational wave emission due to anisotropic neutrino emission. Now let's look at where this characteristic band structure really comes from. So where this structure here comes from. Yeah, that has actually a quite well understood physical explanation that's tied down to mode frequencies of the protoneutron star. And it's still temporarily correlated with when you have convective motions around the protoneutron star. Yeah. And this is why I said what we realized is that the convective motions, their primarily role is to excite modes. Yeah. But the gravitational wave emission really comes through protoneutron star oscillation modes. Yeah. So what happens is that if you have downflows impinging onto the neutron star surface, the neutron star surface is convectively stable, so it will resist the overshooting plumes. Yeah. And it will ring, as it were, as a bell that you strike. Yeah, so in technical terms, that's an oscillation mode. And the restoring force for the oscillation mode is primarily buoyancy. Technically, if you classify this mode that is primarily excited and gives rise to most of the gravitational wave emission, is either the neutron star, protoneutron star fundamental mode, F mode, or one of the low order G modes. Yeah. Now you can estimate, if you know how the protoneutron star surface structure looks. This is a bit what we discussed yesterday. So this steep cliff of density at the neutron star surface, that's really the region where this overshooting happens and where these oscillation modes live. Yeah, you can estimate the characteristic frequency of those oscillation modes if you know the density and pressure gradients in that region. And that can be done analytically if you know that this is a roughly isothermally stratified atmosphere. And then the beautiful thing is that you can tie the characteristic oscillation frequency of this region. You can tie that to basic neutron star parameters. So you can tie that to the neutron star surface gravity, Gm over r squared, and to the neutron star surface temperature, which is very closely related to the mean energy of the emitted antineutrinos. It's useful to express it in that quantity because the average energy of antineutrinos is something that you could potentially measure, and you'd get some relativistic correction effects due to gravitational redshift and so on. Yeah. So the frequency of that mode here is very cleanly related to protoneutron star parameters. And if you could measure it, you can actually pinpoint one of the protoneutron star parameters, yeah, or a combination of the protoneutron star parameters. That might be again a good time to allow for a few questions. Yeah, any questions? No questions? You can still ask any questions that you might have on this later, of course. Now, let's ask, however, what we can actually measure.
I have a question.
Yes.
What is the typical and this antineutrino energy now?
So this antineutrino energy, are you asking for typical numbers? So typical numbers would be a few MeV, 4 or 5 MeV, something like that.
Oh, okay. Thanks.
So
yeah.
In the previous slide, where you show this memory effect due to neutrinos,
Yes.
The memory signal is much louder than the oscillating signal. Is that expected?
Yes,
Understood?
but it's of course at very low frequency. Yes.
Yeah. So it's not even impossible to measure the building up of this memory also.
It's very difficult. No one has actually come up with an experimental analysis whether you could actually measure that. Someone would have to look at this rigorously with the actual with an actual detector model. If you just do it naively and compute a signal to noise for this signal, then the problem is that everything depends on how you window this signal. Yeah. So someone who has to understand a bit about the detector signal and maybe can also extrapolate how this tail continues might actually get a short little publication out of that, saying, can we detect this or not?
Hi, so I have a question. Yeah, so how effective these G modes will be, I mean, in constraining the matter equation of state?
Yes, that's also a very good question. I'll show you a bit later how well they might be able to constrain the neutron star. Well, yeah, I don't think I have a picture about how well they constrain the neutron star radius. The trouble with this is they will constrain the radius of, let's say, a warm protoneutron star that's still contracting, yeah, at a given phase when the gravitational wave emission is loudest. You have to do a lot of complicated inference to tie that to equation of state parameters. It might still show you something very interesting because this contraction of a warm protoneutron star is connected to other nuclear physics parameters than the radius of a cold neutron star. So what this is particularly sensitive to is the nucleon effective mass. And you might be able to constrain something, but there are so many factors that are coming into play as well. So the neutron star mass, everything is, the factors are confounding each other. So how well you can actually constrain an equation of state, I would be very careful at this stage. You need good inference studies combining gravitational waves and neutrinos. That I think is really very much of an open question. You'll see different behavior for different equations of state, for sure, because they affect the neutron star radius, but how much you can constrain is a difficult question.
So more specifically, so in this case, the F mode will be more effective in constraining or the G mode, because I think G modes will be able to penetrate deeper inside the core.
Yeah, so don't get too caught up in the mode classification. The modes that are dominating, they just change character, really. The classification changes, but they always live in a similar region. The amplitudes, the wave function always peaks in a similar region. Yeah, it's just that their nominal character changes. Yeah. And the wave functions are non-trivial because the protoneutron star structure is really such that you have a convectively stable core inside. Nothing's really happening there. A convective region in the mantle, and these modes here live in the convectively stable region at the surface, regardless of what the actual mode classification is. So whether it's currently the F mode or the G mode, that's emitting, it's happening, the wave function is living in the same region. So you're sensitive to the same region and the same radius.
Thanks.
More questions about the significance of the ring down memory signals. There might be more of a discussion going on later after this lecture about how you can actually say something about the memory signal. As I'm not a detector person, I should probably not say too much about that before I say something that's not reliable.
I have a question about, so there's a superfluid also inside the neutron stars. Can that also have any impact on the signal, GW signal emitted?
It may have an impact, but the transition to superfluidity would happen at a later stage. So at this early stage that we're discussing, the first second after bounce, you are still too hot to develop any superfluidity or superconductivity. Later on, that will change the nature of the modes in the neutron star cooling phase, yeah, on much longer time scales. That's true.
Okay, thank you.
Yeah. All right. So let's proceed a bit. So I said what you can really learn robustly from the signal is the mode frequency. That's relatable to a physical parameter. But despite the rather stochastic variations in the amplitudes are not completely undetermined either. And there's a physical parameter that actually does come into play. So if you consider the time integrated energy radiated into gravitational waves, that is related to the overall turbulent flux of convective motions that hits the protoneutron star surface. Yeah. So in a sense, the gravitational wave signal does contain information about the intensity and duration of the convective motions, but it's encapsulated in this time integral of turbulent kinetic energy flux, which is maybe not an immediately intuitive quantity, but on a less fundamental level, you can understand it as something that's the overall strength of gravitational wave emission as related to the vigor of convection that excites the G modes and to the duration of the convection in the gain region. Yeah, and one can actually find good scaling laws in terms of this time integrated convective flux, remarkably good. They shouldn't be that good, I think, really. It's really somewhat surprising. Yeah. There was another question about the lecture materials, whether I can send those. All the lectures, remember, are collected online by the summer school. Yeah, so you won't miss anything. So to show you a bit the phenomenology of the strength of gravitational wave emission that results, we already discussed yesterday that, well, more massive progenitors tend to have longer accretion in the explosion phase. They tend to explode more energetically. That's reflected in the gravitational wave emission, which is sensitive to the amount of mass in the gain region and the convective velocities. Yeah. So as a rule, more massive progenitors tend to have stronger gravitational wave emission, and exploding stars tend to have stronger gravitational wave signals than non-exploding ones. Yeah, of course, you might have a massive star that doesn't explode, and it'll fit into this scheme accordingly. Other specific signatures. So I mentioned that the standing accretion shock instability actually has a distinct signal from the G modes that are excited by convection. That's because, unlike convection, which is in itself stochastic and just can give rise to a specific emission band if it excites a G mode, the SASI itself is an oscillatory instability, coherent fluid motions oscillating with a very well specified period. And in case you have models where there is strong SASI activity, you can find an extra signal component that tends to live at frequencies of about 100 to 200 hertz. Yeah, you see here a comparison of two models, one on the left with SASI and the one on the right without SASI. So both have this G mode frequency, increasing G mode frequency with time, but the one on the left has, and you see that even in the time domain, clearly visible emission in this band at around 100, 200 Hertz. And if you see something like that, that's a fingerprint that you actually have these SASI motions. Yeah. So if you observe something like that, you can actually say what the fluid inside the supernova core is doing, which is pretty intriguing. Yeah. It's a bit difficult, though, to relate this frequency here that you see from the SASI gravitational waves to the frequency of the shock oscillations, because you might have phenomena like frequency doubling that complicate this relation. So a bit of a summary of all the signal components that we see if we have, let's say, a star that explodes with both of these components, forced G modes and shock oscillations from the SASI. Here a very massive model where you have the SASI and you actually see that the SASI frequency changes. Initially, it's going up. That's related to the contraction of the shock. And then it's going down as the star expands. So here you actually you see sort of a trace of the shock trajectory actually in the spectrogram. That's not a noisy spectrogram, that's the raw data, by the way. You'll see noisy spectrograms with real detector noise later. And in this case, we also have a very asymmetric explosion, which then makes this characteristic tail signal. Okay. Now, this is what you expect for non-rotating supernova progenitors. If you also allow for rotation, of course, you'll get this bounce signal, but you might also get these triaxial instabilities, which we discussed before. Yeah, so some triaxial deformation in the neutron star or its vicinity might kick in, and then you could get very strong sustained emission that would leave very characteristic signatures in the spectrogram and tends to be actually a lot stronger of what you usually see from convection or the SASI alone. So if you find a supernova and that has an unexpectedly large gravitational wave signal, this might be what's behind it. Yeah. Rapid rotation and some form of triaxial instability. Now, good. The next step will be move on to detectability. And before I do that, it's probably good to again pause briefly for questions.
Hello.
Yes.
So my question is related to the proto-neutron star. Meanwhile, it's still very violent and settling towards a neutron star, and is still showing promising gravitational waves. Can the densities reach at a point where we can like it starts to express quark matter?
That's a very interesting question. That depends really on where exactly the phase transition to quark matter happens. People have different models for that. If you go to a neutron star that is on the way to collapsing to a black hole, so if it accretes to its maximum mass and then actually makes a black hole, then you have to go through this phase transition region. But if you don't get to these high densities, you have to, the nuclear equation of state has to be right to allow for an early phase transition. You might, depending on your nuclear models, but probably this is relevant in models that, in stars that go towards black hole formation or at least come close to black hole formation. So make very massive neutron stars that are almost about to collapse. Then you might get that, and you might get a signal from that both in the gravitational waves and the neutrinos. The neutrino signal from that has been investigated. depends on the assumptions that you make for the nature of the phase transition. I have a slide on that later. For the gravitational waves, that has got people interested just more recently, and is still need to be investigated further, what you could get from gravitational waves there.
All right, thank you.
Yeah. Okay, there was another question in the chat about the nature of whether I can tell something about the gravitational waves could tell us about the nature of the phase transition. Well, possibly, yes. We don't know for sure. There's been one paper on the gravitational wave emission in core collapse supernovae from one model, equation of state model with a first order phase transition that gave quite a burst of gravitational wave emission, but it's necessary to study possible equation of state models more thoroughly to be able to say what the signal would be generically. There have also been some studies of this in the context of neutron star mergers, and the upshot of that is that there, for a first order phase transition, you could get visible differences to a case without phase transition. For second order phase transitions with of a more gentle nature, smoother phase transition, it would be less detectable. In the core collapse supernova context, as I said, more studies still need to be done. Okay.
Hello, Bernhard.
Yes.
I got a question. So in your today's calculation, the deformation you have considered is due to fast rotation, right? So is there any possibility that the oblateness might be occurring due to the strength of the magnetic field?
There is a possibility, yes, if the magnetic fields are very strong, but I think that's a rather hypothetical scenario, because for that you would need the, so basically the only way to get strong magnetic fields, sufficiently strong magnetic fields, is to have, they would have to come from some form of dynamo driven by rotation. And there will be a finite efficiency. So the ordering of, let's say, the energy scale and pressure scale will still be thermal pressure versus centrifugal effects, and the scale of the magnetic stresses will generally be somewhat smaller than those of centrifugal effects. They might be about equal to it. So it's rather hard to get magnetic fields that are a significant fraction of whose stresses make up for a significant fraction of the thermodynamic pressure, unless you also have strong rotation.
Thanks.
Yeah, it's a different matter if you have a very quiet neutron star. So let's say if you have, if you're making a magnetar, yeah, and then you have a cold magnetar sitting around, and that's rotating very stable with a small mountain made by magnetic fields, and you can follow that over I don't know how many zillions of rotation periods. Then even as you know, a very tiny deformation will make a detectable signal. But in the supernova context, to see something from a deformation by magnetic fields, the magnetic fields would have to be very strong, because you just don't get that many cycles of a rotating mountain on your neutron star. The magnetic fields will have other effects, though. So there has been a recent paper about effects of magnetic fields on inertial modes in the first few seconds after bounce. And the magnetic fields do affect these inertial modes and can give rise to characteristic signatures. Okay. Yeah, let's talk about detectability a bit then. So if you put the amplitude or power spectral density of the noise of signal predictions into diagrams of the detector noise, ASD, and calculate a signal to noise accordingly, you get a rough estimate of the detectability ranges. And the upshot is that the detectability range can vary by, well, at least an order of magnitude. And within our galaxy, you might vary from just a few kiloparsecs if you have a very light progenitor model where the explosion happens quickly, little convective overturn. And for typical stars, typical progenitor stars, you probably expect detection distances of the order of 10, 20 kiloparsecs. And for very strong ones, you might actually sometimes even see them in the Large Magellanic Cloud, even with current instruments. Yeah, and with the strongest gravitational wave emitters, you might be lucky with third generation instruments and actually catch them, at least detect them even in Andromeda, if our signal models are right. If you had something like triaxial instability that is sustained over a long time, then maybe you get even luckier. But for, let's say, the garden variety of models, which have just the convection and to drive the G modes and the SASI and perhaps a rotational bounce signal, these are the ballpark numbers that you could reach. And one big problem, of course, is that the bulk of the emission is often in this region of several hundred hertz, so not in the optimal detectability range for current and planned detectors. But there is some good news because we and other groups actually are starting to figure out also whether you can go beyond detection and actually infer signal parameters. And even if you're close, just not so far above the threshold for detection and can confidently detect the models, you can already start to do some inference on the parameters like the total gravitational wave energy or the peak frequency of emission, where, let's say, in this case, most of the emission through the G mode happened. Yeah, and there is some chance that even for moderate signal to noise, so that might mean you could get that even for advanced LIGO for a galactic supernova. You could do some inference and actually pin down the frequency of this dominant mode and time it as well. The big challenge, of course, and this is something that goes beyond my area of expertise, although our group is doing a bit on that as well, is to better extract those signals from the noise. There are, of course, the very technical pipelines for reconstructing the signal that LIGO actually uses. I'm not an expert on that. But the interesting thing is that even noisy data, you see here in the middle spectrograms with raw data, spectrograms with noisy data, and our attempts to actually extract sort of a chirp signal within that noisy data are actually quite promising. And for reasonable signal to noise, not overly optimistic signal to noise, you could actually detect some of the trajectory, recover some of the trajectory of this G mode band. There was a question there in the chat whether LISA will be able to detect the higher frequency range. So LISA as a space detector, unfortunately, will not help us extending this to a higher frequency range. LISA will be on the other side when not much is happening. Yeah. In the supernova signal. there is some discussion here in Australia about a high frequency detector that might help us for certain purposes. So you'd have to talk about high frequency ground-based detectors to help us in this region. Okay, good. So this is about the prospects for detection. Now, in order to prepare you for the tutorials, I should say a bit about what we actually do when we extract gravitational wave signal from simulations. Although this might not be a job that you're doing on an everyday basis, still can't hurt for you to know a bit of that, because you might be refereeing papers on that and you can say, well, this signal looks fishy, so I'm going to ask again how people did that. That's also an important job for you if you get papers to referee. So one challenge in extracting gravitational wave signals from simulations is that, well, on the one hand, many of the supernova simulations aren't really evolving the metric of space-time. And even if you do, the problem is that the wave degrees of freedom are really so weak that you are better off post-processing your simulations by using the quadrupole formula, possibly with modifications for relativistic effects. Yeah. Now the quadrupole formula, if you actually spell that out completely and do it in a more rigorous way than I have written it down on the first slide, expresses the strain in terms of the second time derivative of the symmetric trace-free part of the quadrupole moment. That turns out to be somewhat inconvenient for many purposes, though, because second time derivatives are generally an ugly thing to process in a simulation. So for that reason, you often convert this into a different form, which expresses the strain in terms of, can express the strain in terms of density and gravitational acceleration and the components of the hydrodynamic stress tensor. So the rho VI times rho VJ. You're going to play with that analytically in the tutorials. Yeah. And there are many pitfalls there. This is basically what I want to highlight, because analytically, if you have the quadrupole formula or its variants, they should give you a vanishing integral in case your flow is perfectly spherically symmetric. Yeah. Numerically, it doesn't always do that. Yeah. And this is something that you need to be very wary of when post-processing simulation data. Yeah, the finite resolution might spoil a lot of things. And there are also often pitfalls when doing the time frequency analysis of the signal. Yeah, so the signal components that will be of interest will emerge in the frequency domain or in the time frequency domain. So you get that by doing a Fourier transform or by doing a short-term Fourier or wavelet transform. Yeah. Now, both with the Fourier transform and the short-term Fourier and wavelet transform, there are many things that can go wrong and slightly distort your signal shape. So one particular problem are edge effects. So if you Fourier transform something like, where is it? Something like this, and your Fourier transform thinks this is periodic, yeah, then you actually get a discontinuity in the function that you transform, because you really transform something here that a function that actually looks like this. Yeah. Now that's going to distort the shape of your spectrum. Yeah. If you try to get rid of that by multiplying your gravitational waveform with some window function, yeah, that tapers the signal at the beginning or the end, you might actually taper off gravitational wave emission that is of interest early on. So you might lose this early signal from the post-bounce convection. Yeah. So there are the bottom line that I'm making here is when doing Fourier transforms, regardless of really what scenario you're looking at, always be very careful what you do. Fourier transforms, the mathematics of is a black box, but things like windowing and phenomena like what is known as aliasing are always something to be wary of and something that the user should know about. Yeah. And this is not something that we need to go into in detail here. You're going to experiment with this in the tutorials, doing different wavelet transforms on some signals that I have provided, and you'll play around with that to see how you can coax out the structure from that signal and what can go wrong. Yeah. So I should not go into that too much because some of it should actually be a surprise when you play around with the data. All right. So questions about everything so far, because then after some questions, I'd go on and give you a bit of an intro into the neutrino signal, and we'd continue this next time then, the neutrino signal. So questions on gravitational waves.
Can you go back to the slide named progenitor dependence?
Yes.
I'm just a little curious what happened to the 11 solar mass. If I'm correct, it stopped in between. Just a curiosity question.
This one here. Yeah. So why this stops here?
Yeah.
Yeah, this is just because these guys, Vartanyan et al., stopped their simulation here. Yeah, maybe it crashed or maybe they ran out of computer time.
Oh, all right.
Yes, yeah. Further questions?
Yeah, do we know anything about, I mean, this is probably a hypothetical. So do we know anything about the rates of these supernovae in, let's say, per unit volume of the universe or something?
Oh, yeah. I mean, there's always a ballpark number, which is that within our galaxy, you might expect one every 30 years. Optically, we haven't detected any for a long time. And of course, you have Poissonian noise. But that's still roughly the number that stands based, for example, on measurements of the live radioactive aluminium-26 that's coming predominantly from massive stars. This rate of about 1 in 30 years in our Milky Way. And then there's Poissonian noise. Yeah, is there a preferred, there's a good question in the chat whether there is a preferred direction for the measurement of the gravitational wave signal. Well, if you have a preferred axis of rotation, then you'd probably rather want to sit in the equatorial plane, because if the star remains axisymmetric, you won't see anything. But that gets different if you have rotation and a triaxial instability, because then you might see a lot if you sit along the polar axis. If you have a non-rotating supernova or progenitor, or slowly rotating supernova progenitor, there's really no preference where you want to sit. Okay. Shall we go a bit into the neutrino signal? Just the first bits, and then continue this tomorrow. So in the neutrino signal, we really distinguish 3 different phases, and you're going to see I have them a little later. Probably show them right away, go a bit out of order. 3 different phases there's one from this neutronization burst that we already mentioned yesterday. So as the shock first proceeds into optically thin regions again after bounce, you get a huge spike of electron neutrino emission. Then you get a phase, the accretion phase or an early explosion phase, where you predominantly emit nu E's and nu E bars, electron neutrinos and antineutrinos, with similar luminosities, and a bit less in heavy flavor neutrinos. And then a cooling phase where all the neutrino luminosities become similar. So you see those phases illustrated here in this diagram. The big burst here for a few milliseconds right after bounce. These are the neutrino luminosities for the various species and below their mean energies. The accretion phase where you have an excess in nu E and nu E bar emission over the nu mu and nu mu taus, and the cooling phase where they all become very similar. We're going to understand a bit why they're not completely similar in terms of their spectra and mean energies later. Yeah, but before we actually go into the physics of the signal, I should probably say a bit about the actual detector technology, because, well, now gravitational wave emission detection is fashionable, so everyone roughly knows how gravitational wave detectors work, but it might be nice to have a reminder about how neutrino detectors work. There are a few different classes of neutrino detectors with different strengths and weaknesses. The largest ones in terms of mass and in terms of detector count rates, expected count rates, are water Cherenkov detectors. So in water Cherenkov detectors, examples of which are the famous Super Kamiokande in Japan, which actually detected neutrinos from supernova 1987A already, and its successor Hyper K. And these primarily detect events through the inverse beta decay. So captures of electron antineutrinos on protons that make neutrons and electrons. Yeah. With these, you can construct large detector volumes. Yeah, water is quite nice to handle. And by measuring the Cherenkov radiation from these electrons, you can reconstruct the energy of the neutrino responsible for the event and so on. In terms of event rate that you have to sample your neutrino light curve, you'd nowadays expect about 10,000 in Super K, more than one order of magnitude more in Hyper K, if you have a galactic supernova at 10, 15 kiloparsecs. So primarily you're sensitive to the nu E bars, but you'll get a few events from other neutrinos through other channels, for example, through electron scattering. There's a variation of these water Cherenkov detectors, which uses big blocks of ice, or in the past seawater. That was done prior to this ice cube thing here in the Mediterranean. So ice cube is a big detector in Antarctica, where you have photomultiplier tubes for that will help you detect Cherenkov radiation from electrons that are produced here by inverse beta decay in a huge volume of ice. And that, of course, allows you to construct much larger detector volumes yet than these normal water Cherenkov detectors like Super K or Hyper K. It has one big advantage, though, which is that for the MEV neutrinos, MEV scale neutrinos that you get in supernovae primarily, yeah, you basically get a blip, a detector blip just in one of these photomultipliers. So you can't really follow the trajectories of the leptons that are produced by the neutrinos here. Yeah, and that means that for supernova neutrinos, you cannot actually detect or pin down the energy of neutrino events. And can't even pinpoint individual neutrino events. You just see that as an excess of the dark current in your detector. Yeah, IceCube can do, I would say that this is a bit sloppily formulated. It could roughly do the same things as Hyper-K, but only if you throw in neutrinos of much higher energies. If you throw in PeV neutrinos, which you get from other sources, then this works a bit more like a normal Walter-Cherenkov detector. Yeah, but for supernova neutrinos, it has an important downside. It can't give you the neutrino energy. But you get lots of events. So for a galactic supernova, you get hundreds of thousands of events. Same reaction, inverse beta decay, so you're again sensitive to the electron antineutrinos. Complementary to that, very important detector types are liquid argon detectors like DUNE. So liquid argon detectors are capable of detecting electron neutrinos, and DUNE would give you about 3,500 events for a galactic supernova, allowing you to sample the electron neutrino light curve relatively decently. And then there are liquid scintillator detectors that also work primarily through detect neutrinos through inverse beta decay. A few other channels can be involved as well. They are of moderate size. You just can't pack in that much material there. Could still give you in excess of 10,000 events. So Juno is particularly ambitious. They'd have excellent energy reconstruction and would allow you to get some flavor dependent and species dependent information as well. Good. Yeah, that's what I wanted to say about detectors. Any questions on that? One question there. What is the question?
Hello.
Hello.
Yeah. So I just wanted to know, like, how well is the localization of the sources from these detectors?
Yeah, for the neutrino detectors, well, for something like Super K or Hyper K, you could tell what the direction is. That's a big advantage. For IceCube, you can't. But let's say you won't see it very precisely. It will probably, I'm not an instrumentalist, so take this with a grain of salt. It would probably be interesting enough for the gravitational wave detector community to know some rough directional localization from Hyper K. Might help with that, but if you have an electromagnetic signal, that will be way better.
Yeah, so I have a question from the previous part. So is it correct to say that the EM counterpart from the envelope ejected will lag the GW signal?
Yes, it's correct. That will lag the gravitational wave signal because the optical signal or electromagnetic signal will only start hours after the explosion is triggered, after the collapse of the formation of the neutron star for red supergiants, and maybe in the extreme case, minutes for very compact 1 BC progenitors. That may happen in some cases. You could have stars with compact envelopes, then this shock breakout from the stellar surface would happen relatively quickly, but at least a few minutes. And for the red supergiant progenitors, which form the large majority, you'd expect that after hours or even a day, of the order of a day or so.
So in that case, the GW detection might give you some information about the localization of the source.
Beforehand, yes, yeah.
Yeah, so
Yes.
that can be followed up electromagnetically.
Yeah. Yes. Good. Now, if I probably have enough time to walk you through this complication of flavor conversion. This will be rather superficial because this is really a topic of its own. So I can only apprise you of the current situation and not discuss this in detail. So one important issue when you detect neutrinos on Earth is that the neutrinos might not be in the same flavor state as they were when they were emitted. Yeah, so we know that neutrinos oscillate, and there are some flavor oscillation effects that we now understand quite well. Few parameters still undetermined. So we know that what basically happens is that supernova neutrinos will be produced at very high densities, and at very high densities, their mass eigenstates are changed because the mass eigenstates are changed because of the potential of a potential term from scattering of neutrinos of electrons and positrons. Yeah, and that shifts the flavor eigenstates, and as the neutrinos propagate out of the neutron star, there will be conversion from the mass eigenstates that they live inside at high densities, and the mass eigenstates at lower densities in vacuum. And that transition can have a slightly different character depending on how fast this background potential of forward scattering on electrons and positrons changes. So if it changes very gradually, you get what's known as an adiabatic conversion, and the neutrinos that were produced, say, in mass eigenstate 1 will go completely into mass eigenstate 1 in vacuum. Yeah. Or if the change of the lepton, the potential generated by the forward scattering is abrupt, you might get non-adiabatic conversion, and there will be jumps between the mass eigenstates. Yeah, that is a phenomenon that's quite well understood. There are still some complications. For example, if you have turbulent fluctuations of density in these regions, these resonant regions, as we say, where the potential term for the MSW effect and the matter and the vacuum terms in the Hamiltonian are of similar size. So if you have density fluctuations there, that might affect flavor conversion. But you can get, so I'll just put down some rough rule of thumbs of how the flavor conversion through the MSW effect will unfold. It's basically depends very much on the neutrino mass hierarchy. So for a normal mass hierarchy, or electron neutrinos at the source will completely swap into heavy flavor neutrinos, and the new E bars will survive with a probability of 0.68 in the new E bar flavor state. If you have an inverted hierarchy, then it's somewhat different. Then the new E bars will tend to be carried away into the third flavor eigenstate and not interact at the source as at the detector as new E bars at all. And the new E's will have a finite survival probability. And of course, you get sort of a swap, right? So in exchange for converting the new E bars, say in this scenario, into heavy flavor neutrinos, you'd get heavy flavor neutrinos at the source that will be detected as new E bars in the detector. Yeah. But this is only a rough rule of thumb, really. Yeah. And I just want to highlight that in this scenario, there is one very important unknown here from particle physics, which is that we do not yet know the neutrino mass hierarchy. So we do not know the hierarchy of the neutrino mass eigenstates. Yeah. And that is something that we could potentially actually constrain through observations of supernova neutrinos. But, and that's what I'm going to end with today, there's a much bigger theoretical uncertainty in concerning an effect that has been, well, actually discovered already in the 1990s, but really come into the fore in more recent years, which is that neutrinos can also do forward scattering of each other. And that will also change the neutrino mass eigenstates because it creates a potential for the neutrinos, for the other neutrinos. Yeah. The problem of this is that, well, the potential, this background potential that all the neutrinos will generate feeds back on the flavor conversion of the neutrinos itself. Yeah. And that in turn affects this background potential. So you get a collective problem. The evolution of all neutrinos depends on the evolution of all other neutrinos. And there's also an additional complication in that the potential that you generate by neutrino-neutrino forward scattering depends on the angular distribution of the neutrinos. Yeah. So if that self-refraction term in the Hamiltonian is comparable to the other terms, the vacuum term or the matter term, then you get very complex dynamical flavor conversion phenomena. And people have identified that whenever you have some phenomena like crossings in the neutrino distribution function, meaning that in certain directions, say the electron antineutrinos outweigh the electron neutrinos, yeah, or also new E's outweighing the new mu's at a certain energy or something like that, that generally sets up the stage for some form of instability. It's very complicated to understand what the result of that flavor conversion will be. That has been worked out for some scenarios, but the very general case is extremely complicated and there's no full answer yet. And you can then ask, so what does this actually matter for the neutrino signal in its interpretation? And the answer is, I think we can't fully tell yet when this matters. There's probably good grounds to believe that this collective flavor conversion can have significant effects during the late neutrino-driven wind phase, among other things, because there the matter potential in the Hamiltonian becomes less important compared to this neutrino potential in the vicinity of the neutron star. It's probably relatively safe to say that the burst phase will be unaffected, so this phase around bounce. And what happens during the accretion phase is a bit more difficult to tell. We are, of course, in the fortunate situation that the luminosities of the various flavors are, well, not so different, they're moderately different. Yeah. So you can hope that the effect of the flavor conversion, if there is an instability that does very, very efficient flavor conversion, is not so huge. But here is really a big theoretical uncertainty in the supernova problem that's still not fully resolved. And much of what I'm going to say later on about neutrino emission has to be placed under this caveat. But what I have to say about the neutrino emission, I think I will rather say tomorrow, because we've already gone for 1.5 hours. And this is probably as much as you can digest today. And we can just take any questions up to here, and we'll then continue this discussion of the neutrino signal tomorrow.
Thank you very much, Bernhard. We can take any more questions? Okay, it seems all the questions have been asked already. So let's give Bernhard a big round of applause.
Thank you. So just the plan for tomorrow, I'll finish the discussion of the neutrino signal and continue to move on to the discussion of supernova nucleosynthesis. That will probably spill over to Friday, and then we'll wrap up with a bit of discussion of supernova phenomenology if we still have time for that.
Great.
Great.
Thank you so much. And we will break for lunch now. The participants here on offline, and we'll come back at 5 minutes past 2. It's okay. And people in Zoom land also welcome to join for the tutorials in the afternoon. So we'll continue the tutorials at 2:05. Thank you, and see you soon.